Good morning. I'm going to talk about the optically excited nanoscale domain pattern transformation in barium titanate. Okay. Yeah. So barium titanate is a representative perovskite oxide and widely used and studied to understand the ferroelectricity and its related properties, such as piezoelectricity. And this system have the abundant number of the domain patterns configurations. And its properties is dependent on the configurations. And also, this system, the domain configuration is dependent on the balance of the electromechanical energies. So we can use the external perturbations such as electric field pressures, heat, and aperture strain to change the domain configurations. And recent study about the optical excitations in barium titanate has proposed that the polarization in the barium titanate can be changed by the optical excitations, which means that optical excitation can change the domain configurations. So the optical excitations drive the electron in the oxygen valence band move to the titanium valence conduction band. And there's a several models to explain why the optical excitation can change the polarization, but I would like to introduce one particular model here. It's called the screening, depolarization field screening. So for the thin film system, the depolarization field is quite strong, so excited charge carrier can be driven by the depolarization field. And eventually, gonna screen the depolarization field and gonna change the polarizations. And it has been experimentally proved that the depolarization field screening is quite strong enough to change the domain configuration before. And so to understand the transformations, the kinetic study is quite important. And recently, Dr. Akamas have shown that the optical excitation can change the domain patterns in barium titanate, specifically AC domain patterns. It showed that the optical excitation can induce the surface electric field and make the transformations from the A domain propagating to the C domain propagating to A domains, and he explained this by the optically induced the polarization rotation and domain walk. And he measured the propagation speed of the 2.5 meter per second. But that system has a micrometer scale domain patterns. Our interest is in the nanometer scale domain pattern, and especially the domain pattern transformation between two different domain patterns. So I'm going to address a few questions here, which is where is the initiation site for the transformation, and what kind of cross mechanism can be used to explain these transformations. And the last is can these transformations be explained with the polarization switching like the domain of propagations, or just transitions like the phase transitions. So we have performed a series of the experiments with the sample, the barium titanate, especially deposited on the neobidium candidate. As you can see in the TEM images, it's quite interesting because this system have the two different domain patterns in one system. The AC domain patterns form on the top part, and the AA domains exist on the bottom part in the system. I would like to note that this is not caused by the lattice relaxation along the in-plane direction, because we have seen that in-plane lattice parameter is consistent throughout the system. And this coexistence of the two different domain patterns indicates that the system is at the domain phase boundaries, which is quite great for us to study transformations. And also, these domain patterns have a nanoscale domain periodicities and has a large lateral coherence, which provide us the opportunity to use the X-ray diffraction method to study domain patterns. Okay. Periodic domain patterns give rise to the satellite peak called the domain diffuse scattering around the barium titanate reflections for our case. So as you can see here, domain diffuse scattering is form around this barium titanate reflections. It's just a schematic, not the data. And by using the domain diffuse scattering positions and its intensity, we can study about the domain wall angles and the periodicity and also the population of the domain pattern in the system. But we can expect the kinetic of this transformation occurs within the few nanosecond scale or even the hundreds picosecond scale. So we need to have the really good time resolution to study the kinetics. So the synchrotron time-resolved X-ray diffractions provide the X-ray pulse with the 100 picosecond time resolution, which is quite great for the kinetic studies. And also the station 790C provide the laser system, which is synchronized with the RF signal from the storage ring. And the optical pulse and X-ray pulse are spatially and temporally overlap on the sample. And we use the two-dimensional pixel array detector to collect the X-ray diffractions. And we use the 50 femtosecond time durations optical pulse and use the 400 nanometer wavelengths to excite the charge carrier in the barium titanate. So first, we have built the reciprocal space map for this system to study the domain patterns. So in this figure shows the QZ, QY plane, including the 002 barium titanate reflection and its thickness fringes along the QZ wave vectors. And you can see AC domain patterns arise along the 010 direction, which means this AC domain patterns is aligned along the 010 direction. We measure the domain periodicity and domain wall angle, which are the 77 nanometers and 47 degrees respectively. And also by taking a look at QX, QY plane, we can see the domain diffuse scattering from the A1, A2 domain pattern arise around the barium titanate reflections. And this also arise along the 110 direction or -1 direction. And it means that the AA domain patterns align along the 110 direction, and we have obtained the 110 nanometer of periodicity. We found that the domain wall angle, domain wall in the AA domain pattern is perpendicular to the surface. So to study the transformations, we have measured the total intensity changes of the AA and AC domain diffuse scatterings. So we have measured the total intensity as a function of time. At time 0, the optical pulse arrives at the sample. And we have observed the intensity change of AC domain patterns and also AA domain patterns. So optical excitation increased AC domain diffuse scatterings, while the AA domain diffuse scattering is decreased by the optical excitation. So it's indicative of the transformation from AA to AC, but we have found that the intensity change is quite different. But the X-ray amplitude is dependent on the structure of the domain patterns. We should consider the structure factor different between the AC and AA domain patterns. And actually, we have performed the detailed structure factor calculations and found that the AC domain pattern intensity changes should be 10 times larger than the AA domain diffuse scattering changes. So we can conclude that these intensity changes arise from the transformations from AA to AC domain patterns. And additionally, to make sure these intensity changes really come from the domain pattern transformations, we have measured the same, we performed the same experiment in the system only with one particular domain pattern. So we increased the temperature up to 70 degrees Celsius, and then we found that AC domain pattern remains while the AA domain pattern disappeared. And we measured the intensity change of AA domain patterns with increasing temperatures and found that at 70 degrees Celsius, the AA domain intensity just disappeared. And we did the same thing. We have measured the total intensity change by optical excitations and found that AC domain patterns intensity is not changed by the optical excitation, even with the larger optical fluence. These results support that these optical induced intensity changes can occur in the system with two different domain patterns, and the domain patterns transformation from AA to AC domain patterns is an origin of this intensity change. So we studied the kinetic of transformation by obtaining the fraction change of the transform fractions as a function of time, and we have found that at 0.4 nanoseconds after the optical excitations, it's about 3% of the fraction of the film is transformed, and the transform process is almost done at the 0.4 nanoseconds. So we use Abraham equation to understand this one. We can study the dimensionality of transformation and also the growth rate. Because the transformation process is done within the 0.4 nanosecond, we use the data obtained within that time, and then we fit the Abraham equation and found that the dimensionality equal to the 0.94 and the rate constants equal to 0.06. And the dimensionality close to 1 indicates the growth mechanism is the one-dimensional Planck-Float mechanism. So the Dr. Pan have performed the molecular dynamic simulations to understand the growth mechanism in thin film system. And he found that the dimensionality of 1 means that the nucleate occurs on the surface of the system and make the one-dimensional planar front, and then growth direction is along the outer plane direction through the sample. So we have the pre-existing nuclei, for this case AC domain pattern. We can reasonably think that the initiation site is the interface between AC and AA domain patterns, and the growth direction is downward with the form of the one-dimensional planar front. And this result is quite interesting because we usually phase transitions or domain wall nucleation growth occurs with two-dimensionally, not the one-dimensional. So I think there should be some reasons for why this system prefer the one-dimensional growth, not the two-dimensional. But the theoretical work can help to understand this one, but we haven't done yet. And to understand this switching, transformation mechanism proceed with the polarization switching or the just transitions. So we have measured the domain wall angle change by optical excitation in AA domain patterns. Since the domain wall angle is related to the polarization direction in domains, we can understand polarization switching with the domain wall angle measurement. So this is QX, QY plane, and as you can see before, the domain diffuse scattering of the AA domain patterns arise. And by taking a look at the QZ, QXY plane in this slide, we can find that the AA domain diffuse scattering arise at the same QZ wave vector, which means the domain wall is perpendicular to the surface. And we measure the QG, the wave vector shift of the left and right domain diffuse scattering. So it's quite interesting result because the right domain diffuse scattering, this one is not changed, is not shifted along the QG wave vectors, but the left domain diffuse scattering shift a lot compared to the right domain diffuse scattering, which means that domain wall angle is actually changing. So we convert this information to the domain wall angle changes and found that the about 5 degrees of the domain wall angle is changed. It's quite big number. And we measured the domain wall angle changes as a function of transform fractions and found that with increasing transform regions, the domain wall angle changes increases too. And what we can suggest here that because the domain wall angle is changes, the polarization in the one domain should experience the polarization switching toward the outer plane direction. So A1, A2 domain patterns should be transformed to the A1, A2C domain patterns. I think it's an intermediate patterns before becoming the AC domain patterns. So from this one, we can understand that domain patterns proceed with the polarization switching in one domain. In conclusions, we have found that the optical excitation can induce the domain pattern transformation from AA to AC domain patterns. And this growth mechanism can be explained with the one-dimensional planar front growth mechanisms. And growth direction is along the outer plane direction. And we reasonably think that the initiation site is an interface between AA and AC domain patterns. And we could, by measuring the domain wall angle changes, we found that the transformation proceeds with the polarization switching in one domain in these domain patterns. And this is my acknowledgement. Thanks for my advisor and the group members and collaborator for the X-ray diffraction studies and the sample preparations. And this, I would like to note that this work is supported by the National Science Foundation. Thanks for attention.
Session 4, questions?
Very nice work. I didn't understand, in the beginning you showed some pictures about the distances between domain walls. I wonder whether the number or density of domain walls is kept constant or whether you double it, something like that. What happens when you transform from one structure to another? Did you keep the same number of domain walls? They are just rotating?
Oh, that's quite interesting questions because I think I didn't think about the density of the domain wall because I think the growth mechanism is like the one-dimensional growth mechanism. So I think the domain wall density should be the same, but the domain wall can be growth along the outer plane directions. But yeah, that's a good question, and I think I need to think about it. I think about the density of the domains.
No.
So in the PhD paper that you referred to, and in our recent work, what we seem to see in the data difference is that when you apply light, it decreases the magnitude of the polarization. So do you know if the magnitude of polarization between A1, A2, and AAC is very different or not?
So in the AC domain structure, the polarizations along the in-plane in A domains and polarization along the outer plane direction in C domain patterns have the same polarizations for this case. But I don't know about the AA domain patterns. But I think what we have seen is previously that the polarizations increase along the outer plane directions. I don't know about the in-plane polarization magnitude changes though.
Just a short technical question. What was the wavelength you've been using to illuminate?
You mean the
light
optical pulse? Yeah, 400 nanometers.
That's sub-band gap.
Just below.
It's 0.6 eV. It's not
Just. Yeah.
So how permanent it changes?
Oh, it's recovered actually. So we measured this up to 30 nanoseconds, and actually we have found that within the 1 nanosecond, the domain diffuse scattering recover completely.
1 microsecond?
100 nanoseconds.
100 nanoseconds.
Just an earlier reference, about 10 years before the papers you cited, there's some papers by Professor Ishibashi and myself which give n=1 values for Avrami switching in KNO3 and BZT. So this is not something that hasn't been seen before. And those are